Ladies and gentlemen, I'm glad to welcome you to the Enamena video tutorial about the Desertec concept. First, about my person, I have a diploma degree in mechanical engineering from the Technical University of Clausthal, Germany, and a doctoral degree in natural sciences from the University of Oldenburg. I have been working on CSP, concentrating solar power, for over 17 years. At the German Aerospace Center Institute of Technical Thermodynamics, and I'm working in the Department of Systems Analysis of this institute. Desertec, an element of sustainable electricity supply. The presentation will show the original idea, present the technology portfolio we have available. We will talk about the renewable energy availability, definition of sustainability, and with that definition we will create a sustainable electricity scenario for the future. After that we will talk about the economic impacts and about the environmental and social impacts of such a scenario. At the end I will present the related research and development at the Institute and the Desertec initiatives being underway at the moment. Finally, I will talk about the challenges of the idea. The original idea of Desertec was presented by the Trans-Mediterranean Renewable Energy Corporation and the Club of Rome in the year 2003. It presented a vision about a trans-Mediterranean high-voltage direct current electricity grid interconnecting centers of demand with high density of population, with the best places for producing renewable electricity by solar energy, wind energy, hydro energy, biomass and geothermal energy. After the publication of the Desertec idea, the German Federal Ministry for the Environment commissioned 3 studies from the DLR with the goal of assessing the renewable energy potential for the sustainable supply of electricity and water in 50 countries in Europe, the Middle East and North Africa, taking into consideration the technical option of concentrating solar power. These studies were elaborated between the years 2004 and 2008. First of all, the DLR assessed the portfolio of energy sources for electricity production. In the first place, we found the conventional sources of electricity, coal energy, lignite, oil and gas, nuclear fission, and maybe in the future, fusion energy. These are characterized by being ideally stored primary energy sources. That means they can be used whenever required, in any place. They can be transported easily, and capacity used can be according to the demand. The next category was the storable primary energy sources. They have to be stored with a certain technical effort. They are not as ideally stored as the first category, but they can be stored in a reasonable technical manner. These are concentrating solar thermal power plants, geothermal power from hot dry rocks, biomass energy and hydropower. And last but not least, we have the fluctuating primary energy sources, wind power, photovoltaic energy and wave and tidal power. So the electricity produced by those sources can also be stored, for example, in hydropump storage facilities or in batteries, but the primary energy for the production of electricity differs by being more or less easily stored. That is the main difference between those different sources of electricity. Here are the pictures of the renewable energy technologies. They are all available already. Some are very well-proven old technologies like hydropower. Some are coming up in the latest years, like concentrating solar power with thermal energy storage, seen here, biomass, geothermal energy, wind power, photovoltaics, and very, very newcomers, tidal and wave power for electricity production. Also, the high voltage direct current transmission technology for transferring large amounts at high capacity over large distances is available since many years. For example, this year in 2011, power line was commissioned between the hydropower plant in Zhangjiaба in China and the center of demand, Shanghai. This is basically something like the Desertec idea made in China by European companies like ABB and Siemens. The voltage of this power line is 800,000 volts DC current. The power transferred is 6,400 megawatt. That is the power of about 6 nuclear power plants. The length of the line is 2,070 kilometers. The source is hydropower, and the losses are very small. It's 7 to 8% over the total distance, including the interchange of electricity with the conventional alternating current grid. If one would try to transport so much electricity over the conventional electricity grid over that distance, about 30 to 40% of the energy would be lost. The construction of this line was about 2 years. It started in 2009 and was commissioned this year, and the overall cost was 2.5 billion euros. The next thing and information one has to assess when talking about renewable energy potentials is the distribution of renewable energy in space over a geographic area. For example, what we see here is a map of the yield of renewable electricity from 1 square kilometer of land in 1 year. The black areas you see are the areas with the best electricity yield from a certain technology, and the bright areas, the white areas, are those with the least energy yield from 1 square kilometer of land. So you can see that a lot of biomass can be harvested in the center of Europe, but no energy from biomass in the Sahara, which is obvious. A lot of wind power is available on the coasts, but less in the center of the continents. Geothermal energy at the Balkan, in Turkey, is very well available, of course, in a certain depth, about 5 kilometers deep in the hot dry rocks. Hydropower is available in Scandinavia, also in the Alp mountains, always when it rains a lot and when there is a high difference of height in the mountains. We have a lot of hydropower. And of course, sunshine is very well available in the Sahara Desert, but less in Northern Europe. So if you look at the numbers here in brackets, what we see is the electricity yield, the maximum electricity yield per 1 square kilometer of land area. So you can harvest 1 gigawatt hour, 1 million kilowatt hours per square kilometer and year from biomass. Also the same amount from geothermal energy. 50 times more from good wind parks in places with high wind speed. 50 times more energy per square kilometer. Also from hydropower in the mountains. And from the desert, in a good place, you can harvest up to 250 gigawatt hours per square kilometer and year. This means in order to produce the same amount of electricity per year as 1 square kilometer of desert in Germany, we would need 250 square kilometers of agricultural land from biomass. So this is of course relevant for developing scenarios of future electricity supply regarding the environmental impact and the footprint. Now, if we look at those resources, we have a map of the resource here, the example of solar energy. We have here Southern Europe. We have the mapping of solar energy, and we know the solar energy intensity in the area. Next, we have to see what places are in principle suitable for placing concentrating solar power plants or photovoltaic plants in the area. For example, we have to exclude the shifting sands in the Sahara. They would, of course, be very unfavorable for placing power plants there. Also, steep mountains or agricultural land, like you see here, is excluded for the use of power plants because, of course, agricultural land is very important in the Middle East, North African region. Exclude all these areas, the white areas are left, and we can combine both maps to yield a map of the remaining places for concentrating solar power plants. Now we can add the energy that could be harvested in that sites and find, for example, amount of electricity that could be harvested over the year in a certain location with a certain solar radiation intensity. So if we do such an exercise for all the sources, we get the following picture. We get the total available potentials for renewable electricity from the different sources. For example, biomass in the Europe, Middle East, North Africa region would have a potential of about 1,500 terawatt hours per year. That are billion kilowatt hours per year. Wind energy could have a potential of over 2,000 terawatt hours per year. Hydropower also around 1,500 terawatt hours. The same for geothermal energy. But now if you look at the solar energy potential, the scale here is not sufficient. It would go up to 630,000 terawatt hours per year, well, which is a huge amount of energy which is available in principle in this region. If we compare this amount of energy that is available with the demand of electricity in the year 2000, we find that it is overwhelmingly bigger. The demand in Europe was around 3,500 terawatt hours per year, and the demand in MENA, in the Middle East and North Africa, only around 700 terawatt hours per year in the year 2000. If we look at a scenario for the electricity demand in the future, we find that the European electricity demand will more or less stay constant because the population will stay more or less constant. Economy will still grow and require more electricity, but also the efficiency will increase, and so we can more or less compensate the electricity demand growth in the future. However, if we look at the MENA region, Middle East, North Africa, we see a considerable growth of electricity demand up to the year 2050. If we compare both regions, we see something like a second Europe is growing south of the Mediterranean Sea in terms of electricity and energy demand. In addition to the electricity demand of the conventional power sector, we have additional demand for seawater desalination because the North African states suffer from a severe shortage of water, of potable water, and this only can be overcome by desalinating large amounts of seawater and making them drinkable. And this will require a certain amount of energy, which has been added here to the conventional electricity demand. But nevertheless, in spite of that considerable growth, we see that enough energy is available. Energy is not a scarce commodity, only that the renewable energy sources are up to now not used very well. The question is, how does a sustainable mix of energy looks like? How will it be covered in the future? So the second question is, of course, then, what is sustainable? What does it mean? First of all, we defined a target function for sustainability in the power sector. The target function was composed of three main issues. First, electricity must be inexpensive. That means the electricity cost should be low and there should be no long-term subsidies in electricity. Second, the electricity must be delivered very securely. That means we need a diversified and redundant supply from many options. We need to deliver power on demand at every time over the year. The scenario and the strategy should be based on inexhaustible sources in order not to become exhausted someday. The technologies we use for strategy should be available or at least visible at the moment, and the capacities we need should be expandable in due time. Third, the strategy should be compatible with the environment and also with the society. That means we need power production with low pollution, with considering climate protection issues. We do not want to create risks for health and environment, and everybody should have fair access to the energy or in the total region. Here is result for the total EU-MENA region. In fact, there is such a scenario of electricity supply for each of the 50 countries we have analyzed from the year 2000 until the year 2050. First of all, what we see that in the year 2000, about 5 sources of energy provided the installed capacity for power generation. Only 5 sources. That was nuclear power, that was coal and lignite, oil and gas, and hydropower. Then our scenario changes its shape by becoming much more diversified. In the future, we will have about 10 different technology options to provide power, including photovoltaic energy, wind power, geothermal energy, hydropower, biomass, wave and tidal power, concentrating solar power, oil and gas, and coal energy. Nuclear energy is phasing out in our scenario. That is because the conventional power park in the year 2000 had around 5,000 full load operating hours per year. That means most of the plants were running in base load and continuous power generation during the whole year. And only few plants were applied for peaking power. But this will change in the future due to the fluctuating variable renewable energy sources, photovoltaic and wind energy, that will only leave a few operating hours for the conventional power park. The future conventional power park will only have about 2,000 operating hours per year. And of course, under these conditions, nuclear power plants will not be economically competitive anymore. Most of these power plants will be operated by oil and most of them by gas and a few by coal. A consequence of this electricity mix is that the peak load, which is represented by this line here for the region, is always covered by firm available capacity during the complete year with a 25% reserve capacity on top of the peak load. That means we have 100% availability of energy plus a 25% reserve capacity from failures and outages of individual plants that may happen. So this is a scenario that copes with all the criteria for sustainability we have applied. Now, if you look at this region, at this part of the concentrating solar power plants, you will find here what has been published as the Desertec concept. This is the share of concentrating solar power plants exporting electricity from North Africa to Europe in the frame of our scenario. You see, it is only a minor element of the complete electricity mix in the future. It is a very important element because it's capable of delivering flexible electricity on demand, which wind and PV cannot deliver. But it is only a small element, and the dependency, of course, of Europe on this element will be rather limited. Another element of the concentrating solar power plants is the energy required for seawater desalination in the MENA region, in the Middle East, North Africa, which is more or less of the same size as the energy exported to Europe. And last but not least, this is the concentrating solar power share, which will be used locally, mostly in the MENA region, for the production of the growing electricity demand. So this is a scenario we have found to be compatible with all the criteria for sustainability we have supplied for this analysis. Okay, about the availability and the redundancy of the scenario, one can say that power on demand will be provided by a mix of variable and flexible sources of energy. There will be an increased number of non-correlated energy sources, which will help to diversify the supply. There will be an increased number and a reduced average size of power plants, so the risk of failures will be limited. There will be an increased number of supply regions all over the MENA region. There will be an additional high-voltage direct current grid infrastructure for long-distance transfer, which will add to the conventional electricity grid and thus will provide an addition to supply. Domestic sources will dominate the electricity mix of the future and will reduce the import dependency. Non-depletable sources will dominate the electricity mix. Renewable sources will dominate and fossil fuels will only be used for reserve and backup capacity. The strategy is based on proven technologies and we will not need considerable technical breakthroughs to reach the goal. Now we come to the economic impacts of such a scenario. What we know from experience is that equipment costs decrease with the installed capacity worldwide. For example, if we increase the capacity for a certain technology by a factor 10, we will have a significant cost reduction of the specific price of the electricity installation in euros per kilowatt installed capacity. This is the same for hydropower plants, it is the same for photovoltaic plants, but also for nuclear plants, for coal plants, for gas turbines. Cost goes down if the installed capacity goes up. You could say the cost is reduced if the demand is increasing. Very different for fuel costs. Fuel prices between the year 2001 and 2011 have increased by a factor of 5. That is true for natural gas, for example, from Russia, which has increased from $86 per 1,000 cubic meters to about $400 per 1,000 cubic meters. Also for crude oil, which has increased from $17 per barrel to about $100 per barrel in this period. And for coal, thermal coal for power plants from Australia, we see the same picture. The peak in summer 2008, where the costs for energy were highest, the reduction in 2009 and the regaining of high costs in the past months. So fuel prices go up with demand and with time. And so if you see this, and if you consider that renewable energy are mainly composed of capital costs, of equipment costs, and they do not consume fuel, you get the following picture. We have analyzed now a national electricity mix over time. If it develops in a business as usual scenario, like you see here in the black line for the country of Spain. So in the year 2000 in Spain, the electricity production cost was around 4.8 cents per kilowatt hour. And according to the fuel price expansion in the future, the cost of electricity would slowly go up in the future. That is the black line. Now, if we introduce renewable energy in Spain, according to our scenario, the cost of the electricity mix will be higher, following the red line. Here we will install more and more renewable energies, but here we see the gap is closing again because equipment cost goes down, fuel costs go up, and the difference between the two technologies becomes smaller. And there is a moment where the renewable energy scenario and the business as usual scenario reach the same production cost. But then afterwards, the cost of electricity from the scenario with high shares of renewable energy and still increasing shares of renewable energy will be stabilized because simply the cost of capital goods like wind power parks and solar fields does not increase or even decreases with the future. It is true that renewable energies are more expensive at the moment than fossil fuels, and this is the difference caused for the electricity consumers in Spain by this difference. But if you compare this difference with the cost increase since the starting year 2000, which is that much, you see that most of the cost escalation has been due to the escalation of fuel costs in a 10 years period. The renewable energy investment added something to that, but it is comparably small. So I call this a typical investment. This is a classical investment. You add money, you invest something, you pay more. Yeah, there is this difference here. And later you have a profit phase, which is this difference here, a big difference, by not being forced to pay higher prices for energy in the future. Classical national economic investment. The economic impacts are the following. The economic risk of power generation is hedged by an increased portfolio of sources. There is an intrinsic trend to lower cost and lower price volatility by renewable energy sources. Energy cost stabilization can be obtained through the investment in new sources of energy. Solar, wind energy, biomass are new sources of energy for a country. Of course, it costs to tap those sources, but those sources will lead to a cost stabilization for the consumers. You can also prevent cost escalation from environmental constraints, like, for example, for carbon trade. There is also prevention of cost escalation from a possible future scarcity of fossil fuels. This can be prevented very effectively by renewable energies. And of course, there's the possibility to reduce the energy subsidies of a national economy by introducing renewable energy. Now let's talk about environmental impacts. If we follow the scenario here, we will see the following picture of carbon emissions in the total EU-MENA region, Europe, Middle East, North Africa. Emissions started in the year 2000 with around 2,000 million tons of carbon dioxide per year. And following the business as usual scenario, those emissions would double until the year 2015 to almost 4,000 million tons per year. This is what would be expected in a business as usual scenario. Following the scenario presented here, a further escalation can be avoided, but a reduction of emissions cannot be achieved before 2030, simply because we start here with small shares of renewable energy, and it takes about 20 years to increase the renewable energy share to a significant amount. After 2030, the renewable energy industry can be big enough and grow fast enough to quickly reduce emissions afterwards. And this could happen following our scenario. The remaining emissions will be from oil and gas, supplied in the peaking plants, as explained before, and also for coal plants that will mainly deliver baseload and flexible power to complement the renewable energy sources. Overall, 1% of the UMINA land area would be required for the installations for renewable energy. This is comparable to the transport sector of today in the center of Europe. So it's not little, it's a considerable impact on land demand, but it's 1%, it's something that looks to be achievable. Okay, environmental impacts, summarizing, we will have reduced greenhouse gas emissions from power generation. We will be able to reduce the risk of nuclear radiation and proliferation. There is reduced local pollution from combustion projects. There is an optimal land use explained, about 1% of the land will be required through a diversified mix. And the technologies are mostly based on recyclable materials. Now let's go to the social impacts of the scenario. If we look at a study from the World Bank about the Middle East and North African region, assessing the potential of concentrated solar power in the region from January this year, we see that in a scenario that foresees a 20 gigawatt installed capacity for CSP in the Middle East, North Africa by 2025, there would be around 200,000 jobs only in the CSP sector. And of course, in other renewable power sectors, more jobs would be created. So this is, of course, a significant positive social impact on the region, which is suffering from a significant unemployment. So, social and political impacts, job creation in UMINA. There is also conflict prevention between Europe and Middle East, reducing the pressure on fossil fuels. Remember, if there would be a second Europe south of the Mediterranean in the year 2050, there's a high risk that there would be conflicts between the Europe and the MENA region about fossil fuels, so alternatives must be found in time. There's also conflict prevention in MENA, solving the energy and water scarcity the countries are already suffering from. There is a conflict prevention in Europe, increasing the energy diversity from a few imported fuels to a big number of the mostly domestic fuels, renewable energies. There is a reduction of European energy import dependency, but also there's a reduction of energy import dependency for countries like Morocco or Jordan. There are additional energy corridors for European supply, like the power lines running from North Africa to Europe. These power lines would not substitute any infrastructure in Europe. They would not substitute the existing electricity grid, but they would add to it, and thus they would add to the energy security and energy supply of Europe. Possibility of this vision is to initiate a Europe, Middle East, North Africa partnership for energy and water, like the Montan Union that created at the end the European Union. Maybe such a union for energy and water could create a bigger union around the Mediterranean Sea. Now I will come to some research and development activities we are developing at the DLR, Institute of Technical Thermodynamics, to support and provide information for the Desertec concept and for the countries that want to work on this. For example, we are developing a solar energy atlas for the South and East Mediterranean countries. The countries that will be provided with data can be seen here. The data will be based on 20 years of direct normal irradiance and global horizontal irradiance, both for concentrating solar power plants and also for photovoltaic systems. The maps will be accessible by a public internet portal where people will be able to download the data. The project was sponsored by the German Federal Ministry for the Environment in its International Climate Initiative program. And there is a big European consortium at the moment working on this and trying to end the project and provide the service by the end of 2012. The project is coordinated by DLR. Here is a website where you already can find some exemplary data. Another research and development we are following is the definition of corridors for solar electricity imports to Europe. You see here an example of such a solar energy map with the site exclusion for the North African region, and you see the green dots, some selected sites for energy production from solar power plants in that region. And here the red points are the centers of demand in Europe where a lot of electricity is required. And so we have made a study analyzing the possible transition corridors for the centers of supply and the centers of demand in Europe with the least economic and environmental impact that can be found. In the meantime, there is a paper available where we have defined the length of such transmission lines, the cost, the losses, etc. So there's a lot of information available already for modeling such systems. Another research and development is about the integration of such renewable energy flows from Desertec in Germany, for example, in the future, in 2050. What you see here is an example of a week in summer. You see here the load of electricity changing with time. You see the composition of electricity production from different renewable and conventional energy sources. For example, what can be nicely seen here is that about 38 gigawatt of power capacity are delivered by flexible renewable energy sources like the Desertec import electricity, import from Norway, from hydropower, geothermal energy, biomass, other biomass sources, and local hydropower. So these are flexible sources here that can provide baseload, and if there is the need, flexible power, reducing the capacity and going up again if needed to complement the fluctuating variable renewable energy sources like wind energy and photovoltaic energy that have to be taken when they come. And there's still some backup needed from gas plants, natural gas-fired plants here, which are flexible but require still some fuel to deliver the power on demand. Nevertheless, such a scenario, here you see a summer week, here you see a winter week with a lot of wind energy available. Such a scenario can achieve a 90% renewable energy share by the year 2050. So this is research and development going on for designing such a future energy system. And the third is a possibility of providing living space in the desert. You see here a situation in northern Egypt, desert, bare desert. And in the future, in 2050, there will be 300 million people more than today living in the MENA region. They will need energy, water, food, labor, and income. And it is really, a good question. How will they do it in such an environment? And one option which is investigated at the moment is the desalination of seawater using solar energy, means developing solar power and desalination plants. Producing water, with the water, there can be agriculture and communal supply of water for drinking water and industry. So there could be communities in the desert living on desalinated water and solar energy. Solar energy is, of course, not a scarce good here in that region. They would have water, they would have food, labor, and income working here. And even part of the electricity generated could be transported to Europe via a high voltage direct current line, creating foreign income for the region. So this is one possibility for a sustainable future supply of further 300 million people in the Middle East and North Africa region. Now, there are concrete Desertec initiatives. At the moment, we have the Desertec Foundation, which was created in the year 2009. This is a think tank which focuses on socio-political aspects and the public information campaigning of the Desertec idea. Here is the website, you can find it. A company, the Desertec Industrial Initiative GmbH, was founded in 2009 too. It has 56 stakeholders and it develops a master plan for the Desertec concept. And there is the Desertec University Network with a lot of universities in the region participating in the meantime to provide research, developing and training. But Desertec still faces some challenges. First of all, the idea requires new structures and new thinking because a lot of changes of paradigm are involved. Renewable energies require long-term financing schemes because they are consisting mainly of capital goods. The concept is based on international cooperation and interdependencies, which needs a very intensive dialogue of different nations. There's a higher complexity involved than using ideally stored fossil energy sources when we have to rely on partially fluctuating variable renewable energy sources. More stakeholders will be involved due to a decentralized generation over a large region. There are, of course, cultural and political differences in the MENA region which have to be overcome. A risk is that lobby groups acting against each other will consume a lot of time talking and not acting. And the main concern is that the speed of environmental change and the conflicts arising in the region will be faster than the solutions provided. So this is, of course, a risk and a challenge that has to be considered. So with this, I finalized the presentation. I want to thank the Federal Foreign Office for funding the Enamina project, and of course all the colleagues from the Institute of Technical Thermodynamics and from the Institute of Solar Research that helped to make this presentation possible. Thank you very much.